Yeah, back up. And now we have here.
And beyond. Thank you.
Thanks, Paul. Let's see. So I'm really happy to have an opportunity to come and speak to you guys about this. This is a very broad field, and I understand that most of you are astrophysics or physics majors and students, but one of the important things about astrobiology is that it's the coming together of the questions about life within our own solar system and beyond into our galaxy, and presumably by analogy into the universe in general. So the way astrobiology is usually shaped up, it really has to do with how life begins, and we have this one example so far, which is us. So how life began and evolves over the history of its planet, on a life-bearing planet. The big question that gets most of the attention is, does life exist elsewhere in the universe? This is, consumes a great deal of not only scientific interest, but of course the public interest as well. And it also extends into thinking about our own planet and what is the future of life on Earth. What is the future of life on other planets? What is the lifespan of a biosphere, as a matter of fact? So one of the things that is really important is that we get very impatient. We want to know more and more, faster and faster, but the scope of astrobiology is truly huge. It's enormous. We are trying to inquire about not only the processes of life here, but how those can be extrapolated to places elsewhere. And astrobiology is still very much a tiny baby science, right? It only started really with the space age, and particularly in proportion to the vastness of the terrain. So astrobiology takes into account things as early in a solar system as its formation and how planets actually form and what one can expect in terms of habitable real estate within that situation. Even the stellar production of life-producing elements. So where do we get the carbon? Where do we get the phosphorus? Where do we get all these other heavy elements that go in to make up our kind of life and possibly others? So I have a very short attention span and a very long attention span, and that I was in love with all of the sciences as a kid, and so astrobiology gave me an outlet for actually doing lots of different kinds of things and putting them into one package. One of the important things about astrobiology is that along with all the sciences that you see here, it has a very large dose of engineering. And this is because either we are looking at exoplanets and there's all the technology that goes into a telescope-based search and the spectroscopy that accompanies that, but also within our own solar system, it involves landed and orbital missions to other bodies. And so the engineering is both a blessing and a curse. It is very expensive and very complex to try to reproduce what we would do in the earthly context about studying life and try to translate that robotically to another body. So we have a lot of challenges in trying to go forward with this. The institute that I head up, the NASA Astrobiology Institute, is a division of a broader NASA astrobiology program. And that started actually in 1965, so it has a very long history, but it was a very tiny program. For a long time when I was a kid, we called it exobiology, meaning biology outside of Earth, and it was kind of considered a hobby science. It was like almost laughable. People would go, oh, ha ha ha, you're studying things that you don't even know exist and whatnot. Nobody's laughing anymore, and they're funding it, so that's the good news. But it's still just as challenging. And so we do a lot with the origin and nature of life, and more importantly, the coevolution of life with its planet of origin. Because when you look at our planet, it's very clear that it has never been separate from its life, not for a very long time. And so the life not only lives on the planet, it integrally has dictated a lot of the chemistry and behavior of the planet over time. And so that puts biology in place as a very powerful planetary force. We have long, both the United States and other spacefaring nations, ESA and the Japanese and now the Chinese space agencies and even other countries like India and China all have their eyes on Mars. Part of that is for eventual human exploration of the planet, but a lot of it has to do with whether or not there were life forms on the planet Mars. Are there any in hidden places on the surface, or in my view, since I'm a subsurface person, in the subsurface most likely. So this is a very active area of exploration. And then, of course, these icy worlds that are the moons around gas giants have proven to be very potentially juicy, and I mean that literally and figuratively, targets for astrobiology. And then, of course, we have the great gift of living in an era where we now know and can observe actual planets around other stars. And so when I was a student, of course, this was still in the realm of speculation. We have a lot of international partners in this, and we have affiliate partners all around the world. One of our most strong associations is in Madrid. The Centro de Astrobiología is a very active center for astrobiology across the sweep from Earth all the way out into the galaxy, and our other very major partners in Australia. So one of the fun things about astrobiology is how deeply international it is. So we could cheat. If the search for extraterrestrial intelligence is actually successful, then it really changes the game. We'll know that somebody else has a biosphere. It may not be quite as simple as just calling them up, but nevertheless, it will solve the question as to whether or not you can have a separate origin of life beyond the one that has occurred here. But short of that, we have to work with what we have right now. One of the things that is always a problem is trying to define life. Nobody has done a good job of this. And one of the problems with a lot of the missions that we've sent to other places is that it's very easy to measure the bulk properties of an environment. But life is not a bulk property. Life is a very discrete, very partitioned, and in many cases heterogeneously distributed process. Even on Earth, where we have a dominant biosphere, our Earth is covered with life everywhere, but even here you see this patchiness of distribution. And so this is an intrinsic difficulty, especially on planets like Mars that don't have any obvious life on the surface. So I have a very simple definition. It's a bunch of stuff doing something that you can observe over time. The problem is we have only our experience on Earth to predict the spatial scale over which this occurs and the patterns that this produces and the pace of life that these organisms that we have here seems to us normal, but it may be very abnormal. So we don't know how to extrapolate some of these things to other places. Well, what is actual life detection? Really, it's finding organisms. So if this canine astrobiologist found a human walking through its territory, it would know, it would see the movement, it would see all of the processes that are going on in that human, and it would know that it had detected life. But we don't have that luxury. So when I was a little kid, I fell in love with exobiology, and this was my idea of it. It was cute aliens that I could have, right? And this is still a lot of what we have in mind from science fiction and movies and stories. But really what it actually looks like is much more subtle and hard to interpret. This is a 1.6 billion year old series of microbial mats from a site in California. So I am hoping to find something like this on Mars or some other chemical evidence or some kind of structural evidence before I finally drop dead. And as I was telling Paolo earlier, I refuse to die until we find that. So I may be very old. So this seems really obvious. What kind of life are we looking for? Well, we're looking for live creatures, if Muppets can be said to be live. And we're also looking for extinct life, right, that is no longer living. There are very big differences here. We can look for fossil materials and geochemical fossils in our solar system because we can actually land on those planets. But for exoplanets, we really have to have a live biosystem because everything we can detect is going to be a disequilibrium product of that process of life there. So finding fossils on other planets until we can actually somehow overcome the laws of physics and get there, I think we have only live organisms, live biospheres to look for. One of the things that I always challenged my students to think about when I was still teaching is how things get preserved. How do you know that something has been there? When we talk about the fossil record, and if you are not involved in looking for fossils, you may not know quite how difficult it is. Things don't preserve very well. So I always ask my students, would we actually know if there had been an advanced dinosaur civilization that preceded us? If you actually go through all of these sorts of ideas of building and structures that would be left behind, and even compare them to the human record that we have on this planet archaeologically, you will see that most of the things that our culture would produce, or a hypothetical dinosaur culture would produce, would have been long since destroyed. And so even the evidence of life on our own planet often eludes us. So what is life? Well, it's a really annoying question because it comes up all the time and we don't have a good answer. We try to define it arbitrarily. People pick the things that they think from their particular point of view and training might work. Some people have said, who cares? Just ignore the question, we'll know it when we see it. That's the opting out version. On the other hand, people like E.O. Wilson have advanced this notion called biophilia, and that is because we are living things, we have, in his view, an extraordinary affinity for life, and so we should know it. I actually think that's true with large organisms. I work in the microbial realm where a lot of them look like minerals, and so I think that that's much more subtle and difficult. Most of us come up with a list of things that life can do and not do. Everybody's list is different, so it's hardly a crisp definition. Can something be observed to live? The process of life is a complex collection of many processes going on at the same time. It's not just a bag of chemicals. And what we're mostly doing with missions right now to other planets is looking for chemicals. So we can say, suspicious chemicals, maybe we should follow up on that. That's still very weak evidence. As I pointed out before, the time constant and the spatial scale are really critical. In a lot of the organisms that I've studied, they take years and even decades to grow. This is something that's very hard to work with for us. We are relatively short-lived creatures. But the consequence of all of this sort of fundamental thinking that really matters when we're trying to figure out life detection missions is, what are the biosignatures that we can really look for? What are those? What are the signatures of life? If you go to Mars someday and you find a big giant dinosaur bone, that's pretty obvious. We think that the likelihood of that is very, very, very small. And so we're looking for things that are much more subtle. So the problems with most definitions of life has to do with really logic and the philosophy of science. People are confusing different levels of analysis. And bizarrely enough, our community hasn't come to terms with something that I think is fairly easy to understand. That is, there's active life and there's potential life. It's analogous to this fundamental distinction within physics between potential energy and kinetic energy, right? One, it resides in one realm. So this is analogous here. I've just put a few examples down. Potential life is probably the information that needs to go into making something that can behave. Where do we put artificial intelligence programs? Well, I would put them sort of here. Viruses are always in contention for this issue because they can direct another organism to do things, but they themselves are not in a living state other than when they're inhabiting a host? What about a dormant seed that's just sitting there twiddling its thumbs waiting for something to happen to allow it to sprout? Can we take this all the way to the other end of actualized life, where the whole of planet Earth is a super being, a mega being? That has been suggested with the Gaia hypothesis, which is something that I've worked on. Don't know if I believe it, but it certainly is a massively complex, non-linear system that behaves with emerging properties that come out of the fact that our planet has life. So it's elusive for us to even figure out what we're looking for, and this is something that affects the astrobiology space missions on a daily basis. So these are the ones that really are out there. The only true slam dunk single observation types of evidence that would really convince us is if you have live organisms. I'm not expecting that as the first thing that we find. Some people are. Or true fossils, body fossils that are sufficiently complex that they're not just a mimic of it that's produced abiotically. Other than that, everything else is weaker evidence. So if you look at extant life that is living now or extinct life, it sort of follows along these types of pieces of evidence. So for extant life, we have great hopes that we can distinguish life from non-life by the complexity of the atmosphere. On our own planet, we have free oxygen, and at the same time, we've got methane and ammonia, which can be oxidized. So that implies that our biology is constantly producing the ammonia and the methane and many other subtle trace gases that we have. This is what we are hoping to be able to see with exoplanet studies. When you look at Earth, we also have a lot of chlorophyll, the green pigment that allows plants and algae and other photosynthetic organisms to actually trap sunlight. That drives our planet. It has been suggested that other types of pigments might be as common on some planets, and maybe someday we'll be able to actually detect those spectroscopic signals. We certainly can on Earth from orbit. We can see that, and people have actually done interesting studies where they tried to look at Earth as a single pixel and infer what actually was going on our planet. If we had a planet that accounted for a single pixel, would we be able to actually tell whether or not it had life on it? And then the stuff further down becomes more and more difficult and more subtle, and really requires you to have a presence on those bodies to actually see what's going on. So really the sum total of all this is trying to write a field guide that you would take out into the field to look for birds, but we're trying to write it for organisms that we don't even know exist, and we don't know any of their properties. And this is a huge challenge. We take into account what are the limits to life on Earth, and over my lifetime that has greatly expanded as we have found organisms in more and more weird environments. And then what is the relationship to early Earth conditions? Because the conditions we see on Earth now are very, very different from the conditions that were present on our planet at the time that life arose. So a cradle for life may not necessarily be the home for life as the planet develops and as life develops. And then of course we try to translate that for what's the potential for life on other planets that have very different circumstances from us. One of the problems that we have in our solar system as we try to do this is that we have only one example, which is us, of what I call a planet type 1 biosphere. So a type 1 biosphere is real obvious, right? If you looked at Earth, you would see all of these evidences of life. The so-called critical zone, which is this narrow band of atmosphere, lower atmosphere, the oceans, and perhaps the Earth's crust down to 5 or 10 kilometers, is where all of the life on the planet exists. And it's a very, very thin layer. But it is driven by sunlight, so it's a top-down critical zone. When we look at other possible targets for life in our solar system, I've been calling these type 2 biospheres, which means that they're cryptic, they're hidden. If Mars had life on its surface at one time, it's certainly not visible now. It is not a planet-dominating process. If there is still life there in the modern era, then it must be subsurface and is not leaving any great traces of itself. And the same for these icy moons around the gas giants. This happens to be Europa, but there are several other bodies like Enceladus around Saturn that are also candidates. In this case, it's not obvious, and this energy cannot be sunlight. It has to be chemical energy. So there are many organisms on Earth, both on the surface and in the subsurface, that make their living not off sunlight ultimately. They actually don't eat organic material in any way, and they don't use photons. They actually perform inorganic reactions. And those inorganic reactions, they couple to the processes of making biomass, making themselves. So if this is true, then the critical zone is inverted. It's coming from geological sources within the planet and feeding whatever biosphere is there in a very different way. This also means, because these are cryptic, that they're not immediately accessible to any way that anyone has thought of yet in terms of finding such things eventually in other solar systems. One of the gifts that we do have is that we know that our own planet has been radically different over time. That it has gone through probably about 7 or 8 giant supercontinental cycles. And each one of these takes about 500 million years for the continents to come together and then separate apart and then smash together again. And this has not been on an exactly regular basis, but roughly it's about 500 million years. And each time that has happened, this has radically changed, of course, the distribution of energy and meteorological conditions and rainfall and even how much area is exposed for life to live around the coast. When you have all the continents smushed together like this, and this is a projection 250 million years from now, this is what's projected to occur in our future, you have great deserts on the interior, which reduces the total amount of life. And you have great big deserts within the ocean where there's very little nutrients, and a lot of the action which happens along the coast is reduced because you have less margin. So we can look through the history of Earth in the rock record and try to see if we can figure out what the triggering events were for big changes in life. What caused multicellular life to happen all of a sudden at 850 million years ago? People have attributed that to possibly the effects of a major global glaciation. So, my own work has really been to try to probe the interaction between microorganisms and their rock environments, as Paula said. And originally, of course, I was doing this on the surface in rock, desert, rock varnish, and travertine deposits, and hot deserts and cold deserts, and all of those kinds of things. And then I got interested and wrote a paper with several colleagues in 1992 suggesting that the best place to look for life still living on Mars would be in the subsurface. And we were looking for some way to get into the subsurface. And drilling is really expensive. And we were all very young at the time. We didn't have the resources to do that. So we got interested in caves. So this is my simple physics version of a cave. It mostly has to do with a boundary condition. There's a strong boundary condition effect in caves, even caves with big openings. It doesn't have to be a sealed system. And this boundary condition greatly affects how materials and energy flow. And it greatly affects physical properties like the temperature and the humidity. So the planets beneath our feet, there are many of them, and each one is a cave. So caves are wonderful because you can get in them, but they're an accessible part of what is a much greater part of the biosphere. So aquifers that store rocks, mines, which are actually sort of human-created caves, and the entire ocean floor, rock fractures, and even ocean caves really are part of this great rock habitat. It's now quite clear from work that has been done by a number of different teams that the total biodiversity of the subsurface is many orders of magnitude greater than the surface. And this is because these are all chopped up, right? So transport mechanisms between one compartment and another is much more constrained. The young lady standing here is standing on an amazing formation. This is in central New Mexico, not terribly far from where I used to be at the university there, and she is standing on Snowy River, which is a sparkling mineral deposit in an ancient subsurface river passage. And this is the largest single cave decoration in the world by many orders of magnitude. It goes on for, I think this latest season of exploration is 19 kilometers and still going. 19 kilometers and still going. But the thing that interests me are all these dark streaks on the walls. These are patches that look like minerals. Ooh, better not do that again. Patches that look like minerals but are actually microorganisms that are processing and extracting manganese, the element manganese, out of the rock material. And within the system itself here, if we core down in through here, we find all kinds of microbial fossils. So the message about this strong boundary condition is illustrated so excellently by work of colleagues of mine, John and Susie Pint. Susie is Mexican. They live in Mexico, but they have done a lot of work in the Middle East, particularly the empty quarter, the Rub al-Khali, which crosses a bunch of different countries, Saudi, Oman, Yemen, and UAE. And the important thing about that is that it's this extremely dry surface desert. You can see the background picture shows that. It has been a desert for at least 20 million years. This is a very old desert. But within that, there are many caves, and you can see a picture of Susie actually peering down into one of these. And if you can see, maybe not from the back so well, but this is rigging here, and there's a caver rappelling down into this very big opening here. And when you get into these systems, what you find, what you find is diveable pools, right? So even though this is incredibly hot and dry on the surface, the subsurface is an entirely different world. And it contains microorganisms, but also higher organisms that have been trapped within this environment for a very long time and have gone off on their own evolutionary pathways. This is true even when you have big giant holes. So the thermal stratification that you can have in a cave is quite extraordinary. And caves have very particular properties because of this. So this is a list of things that are either challenging or not challenging or benign. So the fact that there's no sunlight past the twilight zone, which is what you see there, that's the entrance to Lechuguilla Cave in New Mexico. They have high humidity because they're closer to whatever water table is there. And they have relatively constant temperatures. Now you have caves around the world that have temperatures ranging from extremely hot to sub-freezing. But within any given cave, the temperature fluctuation is usually less than a degree once you get away from the entrance. So those are very benign conditions. If you're an organism and you have a constant feature of your environment, you don't have to adapt to changeability in that. But you pay the price for that because there's low organic nutrients. All of the organics that are coming from the surface, you only get what's left over. So it's residual material. But they are mineral rich, and so this is a place for organisms that use unusual chemical sources like hydrogen sulfide gas or methane, or can manipulate minerals to get energy out of them. This is where they shine. The other aspect of the subsurface is that there's no surface weather. That's pretty obvious, but the consequence of that is that you get great preservation. So what happens in a cave stays in a cave and is quite interpretable within that within that framework, much more than the surface. You can see this because most of the great findings of Neanderthal material, for example, out of which people are now sequencing the DNA, those specimens are found in caves because they preserve so well. So this summary slide shows some of the themes that have emerged from our work in many, many caves. And one of the things that's very important is that there are similarities in these systems that don't depend on the chemistry. There are caves that are rich in copper, caves that are rich in iron, caves that are rich in various other things. It doesn't matter, and it doesn't matter who the players are, it doesn't matter which particular organisms, that they ways of making a living are filled, and the ways the organisms interact and what they do to the environment is very similar. The other point that I want to make is that none of these microbial strains do this by themselves, that symbiosis, that is coming together of many different kinds of organisms, sort of functioning as a big superorganism within microbial mats, is the way they do things. This is how they pool their capabilities to actually transform the geology of the environment. One of the things that I mentioned before, which is very challenging, is the very slow growth rates. But also, along with that, because this is a low potential energy environment, is that they tend to be even smaller. So if you brush your teeth in the morning and you capture some of that and you stain those organisms and you look at them, you'll see that they're about 1 micrometer on average, right? Which is about 1/100th the diameter of your hair. If you look at a lot of the ones that we find, they're even smaller. They're less than half that size. To the point where you wonder how you can pack all the machinery in there to actually have life, but they do. And these are independent living organisms, they're not parasites. So they're making a living with much less interior contents. There's this huge biodiversity. And this is not what I thought when I first started working in caves. I thought it was going to be like a desert, where in a desert you have a smaller number of species of large things spread out because they have to share the resources. But in the subsurface, it's quite the reverse. And I now understand, I think, that it's really the partitioning, the physical partitioning of the subsurface, where you have permeable rock layers and impermeable rock layers, you have faults, you have all sorts of inhomogeneities in the geological environment, and that creates that. And then as a consequence of all of that fun stuff that they're doing, because they're manipulating the minerals, they are reprecipitating them on themselves. So this is kind of a process of self-fossilization. The closest analog to this on the surface that I can think of is a coral reef, where the founder corals grow, and then new baby corals grow on them, and that kills off the older ones, and then they make the big coral structures that way. Well, that's true on a much smaller scale in the caves. One of the manifestations that we've studied quite a lot is a type of biopatterning. It looks like a hieroglyphic pattern, or in dots. And this we first observed in a cave, and I thought, oh, this is a weird cave phenomenon, I don't know what's going on. But then we started to observe it other places, right? We first found it in a sulfuric acid cave. It's dripping with sulfuric acid, so we thought it had something to do with the weird chemistry. Turns out, not at all. We've now found it on Mayan ruins. We found it in mines, caves of all different chemistries, including the lava tubes, even on desert soils. The patterns are very similar. And even higher vegetation in deserts, we've now seen these patterns. And so we've done a series of modeling studies using cellular automata kinds of equations, where it's nearest neighbor interactions, and we can produce these patterns. And now what we're trying to do is take those equations and back out what the actual processes are that's controlling this. So these are macroscopic. You can see these easily with your naked eye. And we have suggested that this would occur no matter what the chemistry of the organisms were, because it's a reflection of how they organize themselves in nature in order to get the resources that they need, and how they interact with each other. So one of the applications of the cave stuff, besides understanding the basic ways that these guys have of making a living is to actually imagine what kinds of caves may occur on other bodies in our planetary system. We know that there are lava tube caves that are a byproduct of volcanic activity on a lot of bodies. The Moon, Mars, Io, Venus, and more. So that's what we know so far, and that's pretty new information over the last decade and a half. But we do know that any planet with a surface will develop cracks. And those cracks can come from internal planetary motions, something like tectonics that we have here, or some version of it. But it can also come from external impacts. And we know that bodies in the solar system have experienced a large number of external impacts. And once you have cracks, the cracks themselves can provide subsurface environment. But also you can dissolve some of the rock if you have the right solvent. And there may be other cave formation mechanisms that don't even happen on Earth. One of the ones that we've considered is the fact that every time you have a comet come through its perihelion, it heats up, of course, and volatilizes a lot of its volatile material, and that creates cavities. So I suspect that there's a lot of space within the interior of a lot of comets. We don't know that for sure yet. But we're trying to stretch our imagination. One of the pieces of work that we have done is looking at the giant moon around Saturn, Titan. And Titan is a very bizarre and fascinating body. It's got a lot of organic material on it that has been produced by reactions within its methane-dominated atmosphere. But when we actually look at Titan in radar imaging, it looks very similar to the kinds of terrains that we have in limestone here. Even though the temperatures are radically different, the solvent is not water, it's liquid alkanes, and the bedrock is water ice with a thick coating of this organic goo. So the chemistry is totally different. This went against my original thinking because, you know, as a biologist and geologist and atmospheric chemistry person, a lot of my training is really focused mostly on chemistry. And I have now become a believer in the fact that in planetary processes, it's actually the physics that dominates, and that you can use a wide variety of solvents and solid materials to produce a lot of the same landforms. So we've known about the lava tube connection since the Apollo days. This is an old Apollo image of the moon from the Apollo era. And it was published in 1969, this breakthrough paper analogizing these features on the moon to what we see on Earth. And if you have seen in the news lately, Hawaii is undergoing a massive new eruption. So we have laboratories for this kind of thing on Earth in Hawaii and Iceland and many other places. So when we look around the solar system now, this is what we see. We have lots and lots and lots of pit craters and what are known as lava tubes on the moon. That wasn't confirmed until 2009, even though it was suspected as early as 1969. That's what new missions will do for you. And then we have in excess of 2,000 of them that have now been identified on Mars. I love this one because it looks like an insect trap, right? It looks like an antlion trap. But also when we look at reprocessed Venus data from the 1990s, and this is dark in here, so it's hard to see, but there's a sinuous rill that is covered right in there. And even in the bottoms of craters on Mercury, of all places, not suggesting that there's life, or certainly life as we know it on either Venus or Mercury or Io, which is very sulfur-rich, but the point is that it's not hard to make caves volcanically, and it's maybe not hard to make caves in other directions. Just to give you a sense of scale, this is one of the high-rise images of one of these pit craters. It's more than 100 meters across, and that makes it immense. If you stick a soccer field on it, that's about what it looks like. So you could maybe rappel down in there and play a game of soccer on the base of it. This is a similar feature on Earth, except of course it's covered with green stuff since it's in the tropics. This is in the Galapagos Islands, and this is about 80 meters. So somewhat smaller than that feature, but geologically very similar. And if you look at the other side, you can see a few little tiny people. This is actually looking at about a quarter of that, because that's all I could get a shot of. So these are immense structures. Well, if you've been to tourist caves on Earth, you mostly will have been in limestone caves. But the truth is that caves occur in many, many different rock types. Big, thick deposits of salt in the Atacama Desert. These are some of the scariest caves because salt pops when it warms up in the morning, and then it pops when it cools down at night. And cavers do not like to hear the sound of popping rocks, right? Because it means that your rigging might come off. This is a time-lapse photograph of folks walking down a lava tube with their cave helmet lights on. So you can see that stream of them walking through. In northern Spain and northern Portugal, we've done some work on granite caves in these big granite massifs. Those are not dissolved, they're actually mechanically released, and then the granite is decompressed, and then that causes spalling of the material. Even in quartzite, which is normally not very soluble, but when you add biology, that makes it much more soluble. This is one of my former students, Aaron Curtis, who did his PhD work on ice caves around Mount Erebus in, in Antarctica. You can get caves in gypsum. So gypsum is calcium sulfate. It's what wallboard is made out of. And it has many commercial uses, but caves can occur in that. And some of the biggest ones in the world are in Ukraine, and even in marble. And then there are a whole lot of caves that are inundated with water. So you can have caves in just about any rock material you can think of. Let's see. This, I just want you to look at this, okay? Not all that. So it's important to sort out in your mind all these different kinds of caves, right? So they've been called many different things, and it's very confusing. So what we tried to do was put in a high-level way of understanding these. For example, if it's a cave that's produced by crustal motions, then it's tectonic. If it's any solid material dissolved by any solvent, then it's solutional. If it's the result of melting or freezing back out or sublimation of some kind of solid material, it fits in here. So this joins both caves in ice and lava caves together, even though they're very, very different temperature regimes. So we're trying to bring, some kind of systematization to this. When we think of icy satellites, I don't think of them as ocean worlds. I actually think of them as planet-sized aqueous caves because they're roofed, right? This is bedrock. It's icy water ice bedrock, and that is covering an interior liquid. And to me, the dynamics of that are much more similar to a cave situation than what we are calling them, which is interior oceans. An ocean, to me, is an open, unroofed system that is in communication with its atmosphere. And this is really a different situation. So if you look at something like an icy satellite and you slice it in half, most people have been thinking about the water ocean on the inside, but that's really hard to get to. That's hundreds, perhaps, of kilometers down. We don't currently know how to get through 100 kilometers of ice and get to anything. But there are many other places within that icy crust that could be melt cavities or surface towers or pressure melt lenses. There's a lot of other things that could be going on in that ice that might be of astrobiological interest. We don't know, but it would certainly be easier to get to. The analogy for that is really in Earth's poles, and particularly the South Pole, but not exclusively. This is Aaron Curtis again in that picture. These are all these towers that occur over ice caves in Antarctica. And these are potentially seeable. They're not huge features, but high-resolution imaging could actually show those. This one happens to be Mount Rainier in the US in the state of Washington. So these features are definitely potential subsurface habitat on those bodies. So the biosignatures getting back to that again, occur at many different scales. And the one scale alone is not enough to actually tell you that there's life there. This is in Sardinia, which is one of my favorite places to cave. And this shows this blue material. And it is a copper transformation material, but it is driven by the action of microorganisms. So if I see something like this anywhere else, I'm very suspicious right off the bat that microbes had a hand in that. This are beautiful little hexagonal crystals, and that was originally a type of iron mineral. But microorganisms have entirely eaten those out. They've transformed that from a less oxidized form of iron, Fe2+, to a more oxidized form of iron as a waste product, and they've gotten energy out of that. So they've entirely replaced these minerals with a different mineral and with themselves, their biomass. I could go on with stories about these, but I don't have time. But when we look at these, and then we look at them up close with electron microscopy, we see all these amazing forms. So these filamentous things here are the microbes, and all of these materials here is the mineral jarosite that they have helped to create. Same thing here in these poof balls. See, this is water actually, a shallow pool, and these big giant blobs of fluffy stuff seem static, but they change over the time course of about 20 years. And when you look at them up close, you see these beautiful calcite, completely unusual structures that we've never seen anywhere else. And all of these filaments in here are the microorganisms, and they only form in the presence of these guys. So macroscopic and microscopic indicators of biosignatures are both important. The preservation environments, this applies, as I said before, to humans. This happens to be from the Antofagasta area in Chile, a mummy of a human infant. But these are the same. They're just microbes and not humans. We find them, buried in rock deposits. We find them in cave pearls. And in fact, two of my colleagues just had a paper come out on cave pearls, these perfectly spherical things that occur in caves, and the role of microbes in producing those. Blue, drippy things like this that we see. This is entirely the result of microorganism activity. So the amazing deposits that you see in the subsurface are very extraordinary. Let me just finish with a description of these different areas. The end of the spectrum that looks at extreme chemistry is represented by this cave. This is Cueva de Villaluz in Mexico, in the province of Tabasco. And it is a cave that has a huge amount of hydrogen sulfide coming into it. That hydrogen sulfide reacts with the oxygen in the water, both in the stream that you can see and on the walls. And this then turns it into very strong sulfuric acid. A lot of the features in here are at pH 0, so they sort of zero out the pH scale. For us, for the organisms that live in there, it's home sweet home, right? So the thing to understand is that we would be stressed in that environment, but this is where they've adapted to. So for them, this is where they want to be. This is where they are. On the other end of the chemistry spectrum is this picture again that I showed earlier. The biggest problem here is the opposite of that cave, because this cave has very little in the way of usable energy in it. And yet, it doesn't have the biomass, it doesn't have the overwhelming amount of life that that cave does, but it's still there, and it's still here in these black structures, and can be grown and can be studied, and probably is only active for a very, very short period of time whenever there's significant rainfall that eventually filters in here. And of course, this is a desert area, so that doesn't happen very often. On the other end of the temperature scale here, this is very cold. This is about -3 degrees. This is another one of these caves, caves on Mount Rainier in Washington. And this has the extra ingredient of not only the cold temperature, but also SO2 and other gases, because those are coming out of Mount Rainier, which is a volcanic mountain. And so that is driving the production of these caves, right? They wouldn't be there if there weren't those fumaroles, but it's also providing potentially oxidizable nutrient sources for organisms. And so that is the cold end of things. And then this system here with all these giant crystals, these are tiny little people here. And these ice suits that we wear in there, because this is super hot, so between 40 and 60 degrees C and 100% relative humidity. We had the opportunity to get in here and study these for a few years, and now it's been reflooded. So their natural condition is to be entirely water-filled. There are no natural openings into these, so they were entirely constructed in the subsurface. And the organisms that live in there are living on the walls, on these orange walls, and they are also trapped within little fluid inclusions within the crystals themselves. Let me just skip forward to that. And finish with this. This is the microbial fossils in those inclusions that got us interested. A friend of mine, Paolo Forti, who's now emeritus at the University of Bologna in Italy, is one of the world's great cave mineralogists, but he's very interested in microbes as well. And he sent me these and he said, "Do you think these are microbes?" And I'm like, "Absolutely, I know that they are." So that got us interested in participating in these expeditions. And then what we found is not only are there fossils, but there are all these little thread-like microbes that are studding those orange walls and in fact diving in and out of these iron oxide clays. And then that's a typical fluid inclusion. They're very huge. You don't usually get that much space within. And this has turned into a time capsule for the microorganisms that are trapped in there. So we know how old the big crystals are. That has been calculated and dated. And we were able to drill in far enough to get about 50,000 years depth, time proxy. And we were originally just trying to get DNA out of these that was sequenceable so we could see. But we wound up being able to get 65 plus actually live cultures of organisms. So what that says is that the organisms have been trapped in those fluid inclusions during the process of those crystals occurring over time. So this got us thinking about, how long can organisms be dormant and waiting for times to get better in geological materials. Some people have suggested even hundreds of millions of years. We haven't made a claim that bold, but certainly over the course of tens of thousands of years, we think it's very possible for these guys to essentially go to sleep and eventually wake up. Well, that matters for planets like Mars, because Mars, the tilt of Mars changes a lot, between almost 0 degrees tilt and perhaps as much as 60 degrees tilt over about 100,000 year time scale. And that might mean that it has obliquity, this is obliquity, obliquity winter and obliquity spring and obliquity summer. And so it could be that there's super seasonal cycles. And if that's true, then microorganisms, maybe they come alive every 100,000 years or so and exist for some tens of thousands of years and then go back to sleep. It's kind of a science fiction notion. And yet, when you look into the organisms that are here on this planet, you can see the ways that organisms have adapted to being dormant. So with that, I will end. Thank you.
We have time for questions, and also I'll bring this great microphone to anybody.
So they can squeak and croak. Just yell at me.
So what are the hurdles we have to overcome before we can send an unmanned mission to one of these caves in Mars?
Well, some of it is political, and some of it is, I mean, of course.
I was asking scientific.
Yeah. Accessible caves can be explored by a number of different robotic techniques. So I have worked with a number of different robotics groups over the years. We've come up with ideas of like little spherical hopping microbots where you can make 1,000 of them and lose 90% of them and you still got a mission. I like that idea. Crawlers, climbers. I'm now working with a group at the Jet Propulsion Lab that has what's called Lemur, and it's a climber. It's kind of big. It's like 20 kilometers, or not 20 kilograms. One would like it smaller, but it has fish hooks like spines in its pads, and it can cling, you know, it does this and then withdraws to hook the feet. And we've been testing it in lava tube caves. People have recently suggested tiny little balloons, which might work on Mars, except the atmosphere is very thin. So I don't know, that could be a little difficult. So we've, you know, come up with a lot of different ideas, not only for astrobiology purposes, but also, you know, we don't expect life to be on the moon other than us, but we'd like to get into the caves there for geological purposes. There has been one proposal that was worked on with sort of a tri-fold suspension mechanism that you can, sort of like a zip line, and you run your guy, and major static robot that doesn't go very far, and you put it down the bottom of some of these pit craters, and then you just passively sense, or you put out some of, you know, your small microbots that can explore. So really, I think it's a robotic access problem. However, there's another group at JPL that is working on seeing around corners in caves, and that's essentially like computer-aided tomography that is used in medicine, where you are calculating what the, you know, very complicated, but the same algorithms, I think, apply, so that you can actually do some reconnaissance in advance. And then ultimately, of course, if you get people on Mars, they're going to have to learn how to cave in the Martian environment, which could be very difficult. So it's really a, you know, an access challenge. Once you get in there, it's easy to study. But caves are unpredictable in terms of their internal geometry. You know, it's not like going into a tube. You can sort of figure that out. Even mines are more predictable. Natural caves are not.
So, would it be possible to find non-carbon-based life outside, like silicon-based? And so, how would we go about it?
That's the question. How would we go about it? You know, we've gotten better and better at figuring out life on Earth, which is great for figuring out life on Earth. But the more precise our search capabilities are here, the more they're finely tuned to what we already know life is like here. And so that puts us further away from detecting really weird stuff. I think that for silicon-based life, you know, you have to hypothesize what the planetary circumstances would be. So it would be, in my mind, a very cold place where you would not have water as the solvent. Complex silica compounds known as silanes are not soluble in water anyway, but they are soluble in anhydrous ammonia, or even high concentrations of hydrous ammonia, and possibly soluble to a low level in alkanes. So knowing something about a planetary environment, you might hypothesize that there would be lifelike processes there that would be based on a silica base. You wouldn't presumably get that in a gas giant, because the rocky interior of a gas giant is probably in some weird plasma state, or liquid with metallic hydrogen, I think, has been proposed and stuff. So it would have to be a planet that had, contact with rocky material. We don't know how to look for it. I think structurally, that structural objects that look suspiciously different from the background would be candidates that you would look at. And then maybe if it was silica, which these silanes are have a much lower reactivity, you would imagine that the life would be very slow. And that would be a giant problem for us because we don't live forever, right? And our patience is this small, and our funding is, 3-year chunks, right, or something like that. So we have an inhomogeneity in the science with the way we actually do our science right now. In fact, that's a big problem for any of these organisms that take a long time to grow, or even a long time to do anything. People are working on whether or not you can tell a difference in thermodynamic state of an object at a microscopic scale, so that you could go, oh, well, it's different from the background, it must be doing something, even if those time constants are real long. So it's a real conundrum to figure out how to, really look for such things. But it's on the radar, and other weird things too, made out of other stuff.
Maybe the other microphone's there. There are 2 questions.
Yelling seems to be working the best of all.
I was just wondering if there's 100% consensus on the fact that these fossil-like, life-like signs in these Martian meteorites are totally of non-biological origin.
Well, there's 100% non-consensus, I would say. It's extremely contentious. And I think we learned a huge lesson from this, and that is even with 5 lines of evidence, each one of those 5 lines of evidence can be explained in a different way. And so the overall strength of the evidence, either for or against that being a biological interpretation, is still very mushy. I think that, the biggest handicap is the fact that that material has been reworked so many times. I mean, first of all, it had to get blasted off Mars and all of those effects, and then it hung around, in orbit for a long time, and then it had to undergo, entry changes. So the material has been reworked a lot. And so that muddies the waters even further. It may not mean that every meteorite would be so compromised, right? So we now have quite a lot of SNCC meteorites in the world meteorite, cadre. So whether people are brave enough to undertake trying to look for those same things is a matter of, how risky do you want to be with your own career? Because the folks that did that work took a lot of heat. First it was a big deal and everybody was excited, but then of course, everybody moves in and does what science does, and that's, to examine the evidence. I think that some of the things that were said about it were silly. So one of the things that was said was, oh, the little wiggly thing that you can, the little worm-like thing, it's too small to be an organism. And I'm like, really, it's not. It's definitely small, but what do we know? But it is just morphology. And, all of the other chemical lines of evidence are equally, maybe they are, maybe they aren't. I think that within that meteorite, the single domain magnetite crystals are more convincing than anything else, because on Earth we only see those in living things, in magnetic bacteria. But people have made kind of things that kind of look like that abiotically in the laboratory. So still up in the air. I think the best way to solve that is to actually go to Mars and do the real work before things get blasted out.
Okay, thank you.
Sure.
Actually, also my question was about consensus. If there is any scientific consensus about the origin of the organic molecules on Earth? No.
In fact, I was just at a meeting on carbon in the solar system, and we don't really know. I mean, there's the initial endowment that you would expect from interstellar dust grains. The interstellar medium has, significant reactions that go on. So there's that initial endowment. How much of that stuff can survive the process of accretion and all of those early solar system processes? Does it all get destroyed and then you have to start from scratch with a planetary endowment? There's a lot of interest in that, and now I think some more funding, at least in the US, is coming into that field to try to answer those questions. Certainly on Earth, we know that the early Earth had a lot of processes that could give rise to organic materials. And so when you look at Titan, and now when we look at Pluto, which has a significant organic endowment. So clearly we know that there are planetary processes that can do this. But the actual history of that material, do we inherit any organics from blown up stars and their solar systems? Nobody knows. So there is completely not consensus. And in fact, most people are honest enough to not have a strong opinion because the evidence is just not there.
So a question a bit going back to the evidence on the meteorites from Mars. So if you are able to go out Cape to Mars and see take pictures, how sure can you be that all the patterns and things you can see there are biological and cannot be explained by...
Yeah, it's very difficult. One of the things that I collect basically is abiotic processes that look like they can mimic life, right? I mean, it's very important for us to build up an atlas of things that we see here and study and go, oh, that looks so biological, whatever that means, and then determine that, well, no, it's not. Or it can be sometimes and not other times. So that whole issue of false positives is something that we're trying to pay attention to. It's not simple unless it's something wiggling around and waving high. It's going to be very difficult. And if it's in the microbial scale, which we are expecting, it's going to be even more difficult. So trying to always keep that possibility of a confounding false positive in mind is really important.
So you don't expect to find a 100% proof that you have something biological, at least right now?
Only with a bunch of different lines of evidence. Okay. So if it looks like life, it's got complicated compounds, it seems to be taking energy in and putting some kind of waste material out. It looks more ordered thermodynamically on the inside of it than the outside of it, whatever that means. Mm-hmm. And if you could somehow watch it make more of itself. And if you had all those, I would say, good candidate. Short of that, tantalizing, but a maybe. Worthy of further study and more proposals to be written.
Okay, well, time for maybe 2 more questions. If there are, otherwise, yes, over
there. It would be difficult if we discover life in planets. It would be difficult to take it from there to the Earth to study it here, or it will be easy?
No, it will be very difficult, and this is for a complicated reason. It's not only scientific but also legal. So the 1968 Space Treaty was signed by 100 and something nations, I forgot. And one of the articles in that treaty has to do with what you're talking about, which is called planetary protection. So there's 2 aspects of planetary protection. One is we want to make spacecraft going to other places that are potentially inhabited as clean as possible so that we have scientific veracity, right? So that we can show that what we find is really there and not just earth bugs. So that's called forward contamination. The other thing is when we bring specimens back here, that's backward contamination. And even though the likelihood of that being dangerous is extremely tiny, this is the only home planet we have, right? So huge amounts of thought and angst and stress has gone into, thinking about how to do that. We have not settled on that. And this is a problem because the Mars 2020 mission, which is probably going to now be the Mars 2022 mission, since its heat shield failed and has to be redesigned. That mission is going to, sample things and then leave those sample containers on Mars with the idea that a subsequent spacecraft, timing to be decided, will go back and somehow scrape these things up and bring them back. we don't have a total scheme for how we're going to deal with those. We don't know whether we're going to build a separate facility. We don't know where we're going to do that. We don't know how this material is going to be distributed, internationally for people to work on it. Will everybody have to come to a facility to work on it? Will we decide it's safe enough at some point where we can actually ship those out to other people? So it's a giant effort to try to figure that out, and it's done in this international treaty obligation setting. And it's dealt with, in terms of policy, by an organization called COSPAR. And COSPAR is an international organization. We're having the next COSPAR meeting in July, every 2 years. It happens somewhere around the world. Last time it got canceled because it was going to be in Turkey and they just had a coup. So it didn't even happen. So politics affects science in many ways. And one of the bodies that meets at that meeting is to try to deal with these issues and try to guide policy. And we're worried now because we have all these independent people who want to go to Mars and do this, that, and the other. And we're wondering, how do these treaty obligations, how do they get imposed on private individuals? It's much easier when you're dealing government to government, but what if Elon Musk actually succeeds against all odds and decides, that we're going to send humans there without all the protocol necessary? So it's a gigantic deal, and lots of money and time is spent on worrying about it and trying to do something about it.
Yep. Okay, thank you very much.
Yeah, my pleasure.
Thank our speaker again.
Thanks.
So if students and postdocs are interested to meet with her in the afternoon, please come here.